Thank you. First of all, I would like to thank the organizers for inviting me. So I'm really grateful. So thank you, Vincent, Philippe, Pablo, Amal. And also I'm grateful to Georgi, who united us here, actually. I would like to tell you about Georgi's contribution to the theory of twisted waveguides. So let me start with the gameplay. Quantum waveguides. I will mention our joint paper later on. If you are in general interested in this subject, I recommend to look at HAL last year. I put my lecture notes from a mini course I gave in Padova last year. So this is a general overview of sort of spectral geometry of tubes in a general setting. So the problem I would like to discuss is as follows. So consider a waveguide. What do I mean? I mean a tube. Yeah, so this is a tube. So omega, I will denote it by omega. It will be a subset of R3 for simplicity, and it is unbounded. And the question is, what's the spectrum? Of what? Of the Laplacian associated to such a domain. And for simplicity, let us take Dirichlet boundary conditions. So this is the general game. Given a geometry of such a tube, what's the spectrum of the Dirichlet Laplacian? And to be more precise, how to define such a tube? So, given the picture, I think you understand you have some cross-section and you have a curve in the space, and you translate the cross-section along the curve. So let me try to formalize it. So the cross-section I will denote by small omega. It will be a bounded open connected set in R2. So bounded, it's the only assumption, no regularity. And at the same time, there is some given curve. I will denote by gamma. And so it is a curve from R to R3. Without loss of generality, we can assume that it is unit speed, parameterized by its arc length. Then the second derivative is just the curvature. So let me use this notation. Kappa is the curvature of the curve. And now you have a freedom, yeah? Now given on, you can translate the cross-section along the curve, but you can also rotate it. So we need some frame. We need to frame the curve. So what do I mean by this? I need, it's not good. I need a triad of a tangent vector, t, and some normal vectors. So T is just the derivative of gamma. So this is the tangent vector. Salut. And okay, there are many choices how to choose such a triad. The most useful choice is as follows. So I will require that the frame satisfies this differential equation. Zero, K1, K2. 0, 0, 0, 0. So this is so this always exists. It is called a relatively parallel adapted frame. K1, K2 are some functions. They satisfy K1 squared plus K2 squared is kappa squared. And this is sort of parallel transport. Yeah, you want to keep that T is tangent. So N1 and N2, they have to rotate along the curve somehow. But they rotate minimally, in the sense that their derivative is tangential. And the advantage is that such a frame always exists for any curve. It is less known than the Frenet frame. The disadvantage of the Frenet frame is that it might not exist. That's why I am using this frame. Okay. So this is a standard geometry, but it is a special frame. So now I would like to introduce an arbitrary frame. So I rotate it. So I introduce N1, N2, I denote it theta, and it will be just a rotation of this frame. Cosine theta minus sine theta, cosine theta. And by using this arbitrary frame, okay, theta, it is a function. And by using this arbitrary frame, I can define omega formally. So omega is gamma s. It is exactly what I said, that I translate the cross-section along the tube. So I have T1 N1 theta s plus T2 N2 theta s, and s T are the coordinates in r times omega. So this is the formal definition, and there is some terminology. We say that omega is bent if the reference curve is not a straight line. So it means that the curvature is not identically equal to 0. And twisted, which is the true meaning of the game of twist, is when theta dot is not identically equal to 0. So you are away from this parallel frame. And of course, even if you are in this situation, the twist might be trivial. Think about a cross-section which is circular, disk or annulus, so then even if you rotate, you will get the same waveguide. So also here you need to require that omega not circular. Okay, so this is the setting. And before, maybe I can write it here. So the problem, as I said, is the Dirichlet Laplacian. This is a self-adjoint operator, and I am not leaving the room in L2 omega. It is defined formally as the operator associated to a quadratic form. The quadratic form is, as usual, just integral of gradient u squared, domain. This is pretty standard. You take the Sobolev space H0, 1, omega. Now the strategy. The strategy how to study such an operator, spectral properties, is natural, is to pass to these curvilinear coordinates. Yeah? So let me use a color. So this operator is unitarily equivalent by using the coordinates to such an operator. I will denote it by H. It will be an operator, okay, if you make the change of variables, it will be an operator in L2 straight tube. You will get some Jacobian ds dt. The Jacobian you can compute explicitly. This is 1 minus k1 theta s t1 minus k2 theta s t2. k1 theta, k2 theta, it's defined analogously to the rotations of n's. And the operator acts as follows: 1 minus 1 over f ds minus theta dot d tau 1 over f ds, the same operator, minus 1 over f gradient t dot f gradient t. So what do I need to explain is d tau. So this is just the transverse gradient. D tau is just angular derivative. So this is tau times gradient t. Tau is minus t2, t1. So now everything is settled. And I think, Georgi was interested especially in the effect of twisting. And I think why he liked it is because it looks like magnetic field. Yeah, it appears like a magnetic field, but of course there is a difference because magnetic field is a first order perturbation. This geometric perturbation is a second order. So the plan for my talk is first to talk about what happened before Georgi started to be interested in this game. So let me call it pre-Georgi's times, or dealt cards for him. Then I will recall results by him and others. By this I mean not me. And at the end I will mention our collaboration. So, okay, so this is like 2000, what did I write? 8, 12, and 12, 18. And please, like what Hanne said, ask me questions immediately if you have. So if there are no questions, so let me start with the dealt cards. So okay, so the starting point, it might be difficult. I think it could be like 18, something like this, no? Laplace. If not Laplace, then a Helmholtz. So by this I mean the case of a straight tube. Yeah, so then everything is easy. So in this case, what do you know is that the spectrum. Okay, let me maybe write it more carefully. When kappa is identically equal to 0, no bending, no twisting, then the spectrum you will find by separation of variables. So the spectrum is purely essential, and it is given by E1 infinity. E1, it is the first eigenvalue in the cross-section. Cross-section. Okay, then a famous result when an interesting study started, it goes back to 1995. And okay, at this place, I'm a bit cheating, but it's normal. At this space, I should mention Duclos and Exner. So let's affiliate this result to Duclos and Exner. So they noticed that if you bend the tube, you will get a spectrum below E1. Yeah, this is the result. So kappa not identically equal to 0, but no twisting. Then the result is that the infimum of the spectrum of H is strictly less than E1. And maybe I should say also, okay, this is a result, this result was expected somehow, but it was in the full generality established only in 2014 with a collaboration with Lou, that if the bending tends to 0 at infinity, twisting tends to 0 at infinity, then the essential spectrum is preserved. So it is the same as in this situation, so it is E1 infinity. So why do I mention this result? Because then this result of Duclos and Exner you can interpret as the existence of eigenvalues. So you have spectrum of H, 0, E1, and you know that the essential spectrum is preserved under this condition, and this result tells you that you have some eigenvalues, quantum bound states, if you interpret the Laplacian as a quantum Hamiltonian in a nanostructure. So this was a famous result. A complementary result was obtained by me and collaborators in 2008. Ekholm, Kovařík, and myself. So it is the opposite situation. Now kappa is equal to 0 and theta is non-trivial, meaning that also the cross-section is not circular. And in this case, we established a Hardy type inequality. H minus E1 is greater than or equal to some constant 1 plus s squared, for example, in this way. So this is a Hardy. The constant is positive, yeah? So in particular, it means that not only that there are no eigenvalues below E1, but you have sort of repulsivity, which is quantified by the Hardy inequality. And to put the results of Georgi into context, I also need to mention two other results. 2004, it was my collaboration with Tiedra, who was also in Santiago. And okay, maybe, so this is in reviews in mathematical physics. This was in an archive for rational mechanics and analysis. This was JPA. And in this paper, we studied the nature of the essential spectrum. So nature of essential spectrum of H via Moore. So Moore, I should also mention here. So we obtained the usual thing. And maybe even more importantly, there is also another result, 2005, Exner-Kovařík. So don't be mistaken. Yeah, this is this paper. It is the first paper about twisted waveguides. Yeah. This one appeared first only because they chose a faster journal. Yeah, our result was first. And what they do is, and this is what I will assume from now on, no bending. And twisting is special. Beta plus epsilon s. Beta, it is a constant. And epsilon, it is a function. And they assume that epsilon goes to 0 at infinity. Then they located the essential spectrum. It changes. It is now, I will denote it lambda infinity, infinity. This is strictly greater than E1. And as a second result, it is of this nature. They have a sufficient condition that if theta dot squared minus beta squared is negative, then you get some discrete eigenvalues. Okay. And this result was later complemented by my collaboration with Philippe Briet, 2015, where we showed that in opposite situations to this condition, we get a Hardy inequality again. Okay, now to the results of Georgi. So his first interest was about this setting, but to get some more precise results. In particular, first about eigenvalue asymptotics. And this is a collaboration. It is 2009. Philip, Hinek, Georgi, and Sukorsi is here. So this is in communications, in PDEs. And so to keep this convention, let's assume that beta is negative, epsilon is positive, and epsilon behaves as follows. So when S is large, it behaves like L over S to the power alpha. L is positive, and alpha is from 0 to 2 to infinity. And the question is, okay, you have eigenvalues, how many? So they answer this question. So actually, in this situation, when the twisting decays to 0 somehow slowly, you have infinite number of eigenvalues. And in this situation, you have just a finite number of eigenvalues. And here it is a little bit more complicated, but they also have results in this critical situation. And they have precise asymptotics. I can write it down, but okay, yeah, depending on alpha, they will get how quickly in this situation the eigenvalues accumulate at lambda infinity. But I would like to focus on the result of joint collaboration with him, so let me just briefly mention this. And the second contribution was about scattering. And this is 2014. But the preprint was much before. It was 2011, so the dates are as I wrote. And this is again Brie, Kovařík, Rajkov, JFA, and they essentially do what we did with Theodora, but for twisted waveguides. We did it for bent waveguides. Yeah, this is important. This is just kappa not equal to 0, theta equal to 0, yeah? So they did it in the complementary situation, in such a situation, and again, via Moore. So they get location of eigenvalues, absence of singular continuous spectrum, and also the asymptotic completeness of wave operators, the usual stuff you get by the Moore theory. Okay. Then there are also results about resonances, but not by Georgi, but by others from this audience. So there is a paper by Vincent, Pablo, and Nicola Popov about resonances, 2018, and 2020, Bruno, Miranda, Para, Popov, also about resonances. So it continued. And finally, let me talk about my collaboration with Georgi. So it started in 2012 when Georgi invited me to Santiago, and I can confirm, as everybody was saying here, that he was very friendly, generous, and not only him, but also I have good memories we spent together with Lily and Georgi. And so we started to discuss, okay, what Georgi wanted to do, and it was the idea that we will do it together. It was about periodic twist. So this was the initial idea. And it was based on a common belief. Let me state it as a conjecture. The common belief that if you have a periodic system, then the spectrum is absolutely continuous. Yeah? So in this case, in particular, if kappa is equal to 0, theta dot is periodic. So you expect that the spectrum, the point spectrum in particular, is empty. So this is a common belief. It was proved for Schrödinger operators. In 2 dimensions, it was proved even for waveguides by Shargorodsky Sobolev. Alex is not here, yeah, unfortunately. Anyway, so this was what we were trying to do. Okay, then the problem was that we realized at a certain point that it has already been done. Okay, I exaggerate a bit. Yeah, we discovered. Okay, it's a shame, but we missed this paper, 2003 by Friedlander. In contemporary mathematics. And he actually did it in a quite general context, in particular to waveguide systems, under some assumption, some extra assumption. It was reflection symmetry. And okay, but even with this assumption, then we were not too much motivated to continue with this conjecture, and also we didn't know how to do it in general. And okay, I should also mention a paper 2018, because we have Alessandra here, Mamani, very. So they prove it for thin tubes. Yes, again some extra assumptions. Okay, so this was sort of a bad news. Yeah, so we couldn't compete. We were not able to get something better than Friedlander did. So then we had to do something else, and what we did was a random twist. And this is a collaboration with Georgi, of course, and Werner Kirsch, who was supposed to be here. It was published in the Journal of Statistical Physics. And the idea was to consider random twisting, Anderson type twisting. So fortunately, I don't need to speak much because we got a nice introduction from Peter Hislop. So just very quickly, so we consider theta dot as xi. So xi, it is the probability variable. It was denoted by omega, but omega is taken for the cross section, so I denote it by xi. And we define twisting as follows. So it was exactly like in this lecture given by Peter. And this W was denoted by U, I think. But we are mathematicians, so we don't care. So lambda k, it is identically distributed independent variable, so I, D. W is smooth. And we assume that it has some decay. So for large S, it behaves like 1 over S to the power alpha. And we always assume that the lowest point, okay, this is the essential infimum, it is greater than minus infinity, it is bigger than the essential supremum of lambda 0, and this is less than infinity. And the first result we have, let me call it a proposition. So if this essential infimum of lambda 0 is 0, then we are able to locate the essential spectrum. Yeah? Almost surely in the usual setting. So in this case, the spectrum is E1 infinity. Almost surely. And then we have a theorem about, should I call it localization due to disorder? Lifshitz tails. So where will I fix it? Maybe here. Okay. So this is the main result. It is associated with the name Lifshitz. Tails. And we assume, in addition to this asymptotic condition, we also assume that these lambdas are not localized at a single point. So let me state it in this way. So the probability of xi that lambda 0 xi is less than epsilon. Epsilon is a small parameter. So this is bigger than C epsilon kappa. C kappa are positive constant. Epsilon is a small positive constant as usual. Then we need some technical assumptions, unfortunately, but okay. So we need that this logarithmic derivative is bounded. Okay, you take the supremum, essential supremum in both variables, S and xi, and it must be bounded. And we also need that the tube is thin. So by this I mean that this quantity, T in omega T, this is small, unfortunately. And we need that it is non-trivially twisted, so we always need to assume that let me state that the cross-section is not circular. Okay, yeah. So it's twisted, yeah. So omega not circular. And in this case, we consider the integrated density of states. What do I mean by this? Let me put it here. Integrated density of states, and E. So it will be the limit when L goes to infinity, 1 over L trace of the counting function. Okay, you take the tube, twisted tube, but finite length, L. Yeah, not infinite, finite, and then you send the limit to infinity. And we get these asymptotics, which are known as Lifshitz tails. When E goes to 0, log n E1 plus E divided by log E. This is equal to minus 1/2 if alpha is between 0 and infinity, and it will be minus 2 alpha minus 1 if alpha is between between 1 and 2. So you get a very fast localization, yeah? If E goes to E1, if you go from here, you get you get some exponential decay. Yeah, and for this, it is indeed important that the tube is non-trivially twisted. If it is not twisted, if it is straight, you will not get exponential decay of this type. You will get some polynomial decay. It is called Van Hove singularity. Yeah, so this is very different. Yeah? This is really important that so the twisting has such a deep consequence. Okay, that's all what I wanted to tell you.
Comment?
Oh, it was so unclear, the talk. Sorry. Thank you.
There was a lot of information, and it was really nice. I was just wondering about this alpha in the last case. This is the decay of the single side potential there. So you needed to be, one could say it's a weak decay, because usually when the simplest case is compactly supported.
Mm-hmm.
But in this case, you needed to be.
We need less than compactly supported. If it is compactly supported, it is included. You mean this W is?
With alpha equals to infinity.
I mean, okay. This will be always satisfied. If it is compactly supported, then it is true with any alpha.
So in that case, you would have the exponential decay.
Yes.
With a weak decay, you would have the Van Hove.
Yes.
And did you try to get some spectral information out of it?
Spectral information. This is spectral.
No. Localization. One usually uses that estimate with localization.
So that's what we have. Yeah. So we don't have any other results in the paper, but it's quite possible that, okay, unfortunately Werner is not here. He would be he would present it much better than me. Yeah? He's an expert in this. I was more on the geometric side. But okay, yeah, maybe one can continue this research direction. But this is the only result we have, Lifshitz tails. There is Leonid.
Are there some meaningful examples of non-trivial simply continuous spectrum, like quasi-periodic listing, something like this?
Simple examples of?
Non-trivial singular continuous spectrum.
Non-trivial singular continuous spectrum for waveguides. For waveguides. I am not aware of. Yeah? I mean, of course, one expects it will be empty. So.
Even if you take almost periodic listing?
Ah, okay. No, okay. There are no results. Yeah, maybe this should be done. Okay, no results, as far as I know, at least. But you are right. Yeah, this inspired by Schrödinger operators. It might be possible to construct examples. If there are no questions, I will have an announcement, which is okay. Okay, don't worry, it will be just a quick announcement, because if you like this place, I mean the conference site, then you are kindly invited to come again in June. I will be organizing a conference in CERM in a better season, not in January, but in June. And it will be about non-self-adjoint operators. But don't worry, we consider self-adjoint operators as a special subclass of non-self-adjoint operators, so everybody is welcome. Okay, thank you.